Okay, so conservation of momentum, example problems. These will be problems that are going over things that we talked about before. Again, this isn't all-encompassing, but what you'll see will be some examples on how to use the chart to solve them. So first example, and I got to get my pen up. First example, we have two carts in lab, and one cart is moving to the right with a mass of 0.5 with the speed of 92.8. So cart A is going this way. It then collides with another cart, cart B, which is traveling to the left. It has a little more mass, but not going as fast. But then they collide and they stick together. And so the question is not only how fast they're going to be going, but in which direction, right? Are they going to be going the negative direction or positive direction? And the math will lead us there. And so this is how we face that type of problem. As we make our chart and we look at cart A before, mass times velocity, and we get 46.4 kilograms times centimeters per second. Again, centimeters per second is fine, as long as it's consistent throughout the problem. Now, cart B, you take its mass, remember it's going in the negative direction, so its velocity is negative, therefore it'll have a negative momentum. Now, we add those two together to get a total momentum in our system of 14. Since momentum is conserved, our final momentum will also be 14. Once I know the final momentum, then I look at what I know at the end. Cart A is traveling at a certain velocity, and cart B is traveling at the same velocity because they're stuck together, so we just use V. So 14 is equal to 0.5 V plus 1.5 V. I add my V's together to get 2 and equal to 14, just a quick division by 2, and it tells me that the velocity is 7, but it's positive, which means both carts are going to the right 7 centimeters per second. Next example, we got a 25-gram bullet entering a watermelon of this mass and embeds itself into the watermelon. The melon and bullet then travel together a speed of 3.82 meters per second with the bullet inside the watermelon, right? So what was the entry speed of the bullet? So we got the bullet here, and we got the watermelon here. Watermelon not moving, but the bullet hits it. And then that leads us to the bullet inside the watermelon, assumably still traveling to the right, I would think. But let's see what the math tells us. The bullet has a velocity before, but we don't know what it is. But we know the melon is not moving. So we know that the initial momentum is 0.025 times whatever the velocity of the bullet is. But we know the momentum afterwards. We know afterwards the bullet, and we want to put our mass in kilograms to match the kilograms on the melon. So we put our mass in kilograms, and we multiply it by the speed of the watermelon bullet combo, and we get the momentum of the bullet. And then we also find the momentum of the watermelon. We add those together, and we find our total momentum afterwards is 9.0725, which means, conservation of momentum, the momentum we start with is also 9.0725. So I know that if I take mass times velocity plus 0, I will get that answer. So taking the 0 out of the equation, I get this equation here, divide by 0.025, and I get a velocity of positive 363 meters per second, which means the bullet was traveling to the right that fast, which is pretty fast, and that's what you'd expect out of a bullet. That's quite a slowdown for the bullet, thick watermelon. Third example, we have a bullet and we have a watermelon, okay? The bullet is traveling this fast to start, but now it goes through the watermelon, and we find the speed of the bullet to be 109 meters per second after it goes through the watermelon. But now we want to know if we have the bullet in the watermelon, and the watermelon is stationary, the bullet is going to go through the watermelon, and we're going to have a bullet here and a watermelon here. The bullet slows down, therefore the watermelon must move. But we don't know how fast that watermelon's moving at the end. So that's what we're trying to find. So we look at that. We set up our grid. We know the melon is not moving, so that's at 0. Before we talk about momentum, the bullet, we know the mass and velocity, so we know its initial momentum. So the momentum of the bullet plus momentum of the watermelon gives us total momentum. Total momentum we start with equals total momentum we end with. We know the momentum of the bullet after the bullet goes through the watermelon, because it slows down. So the momentum goes down. So the momentum lost by the bullet will be picked up by the watermelon. What we have to find is the velocity of that watermelon afterwards. So we take our momentums at the end, add them together, and make it equal to our total momentum. We bring the 2.725 over, and then we divide by 2.35, and we find the watermelon is moving to the right with a velocity of 1.15 meters per second. Another example, we got two carts now. We got cart A moving to the speed and encounters a magnetic collision with cart B that's initially at rest. The cart rebounds with a speed of 45 centimeters per second in the opposite direction. Determine the post-collision speed of the one cart. So when we say magnetic collision, and you'll see this sometimes, cart A and cart B have magnets on each side here, okay? And then instead of touching, when the magnet gets there, it repels. So they repel. The magnets repel each other. So A is moving, B is not. After they collide, A rebounds backwards, but then the question is, B has to push off this way, okay? And we want to know what that is. So B initially has no momentum and gains some, so therefore that momentum that B gains is going to be what A loses as it rebounds. So before we get A, mass times velocity, we know B is 0. Add them together, our initial momentum is 64.5. Now afterward, since we know A goes in the opposite direction, we have to make velocity negative, which means its velocity is now negative 22.5. And then the momentum of B will be 1.5 times V. But that will equal 64.5 because momentum is conserved. So we make a nice little equation here, adding up our right side of the equation, making it equal to 64.5, and we solve for V. We add over and divide, and we get 58.0 centimeters per second. So cart B is moving to the right, 58.0 centimeters per second. Another example, we got a big truck moving rightward with the speed of 5 kilometers per hour, colliding head-on with the car moving leftward at 10 kilometers per hour. So a lighter car traveling faster. When they collide, the crumple zone kicks in, okay, and they stick together. So the question is, what is the post-collision velocity? Again, we don't want to make an assumption that the truck's going to push the car. The math will tell us. So we're going to find velocity, but more importantly, is it going negative or positive? And we're going to know which direction things are traveling. So since we know the mass and velocity of the truck going to the right, we make that a positive velocity. I mean, you can go the other way, but I'm making that positive. Since the car is going the other direction, its velocity is negative, which means its momentum is negative. We add those together to get our total momentum. Total momentum is conserved, so we're stuck with 5,000. Now we look at the truck's momentum afterwards, and since they're stuck together, they have the same velocity, so it's 3,000 V plus 1,000 V, which gives us 4,000 V. And then when we solve for V, we get 1.25 kilometers per hour. So the truck and the car are traveling to the right at 1.25 kilometers per hour after they stick together. Last example, football example, obviously. Goal line stand, we got a fullback moving to the east with a speed of 8 meters per second, and he hits a lineman. Make the linemen bigger because they're bigger guys, moving westward with a slower speed. They collide and stick together, and that means they will move at the same velocity after the collision. So, fullback, lineman, sticking together. Again, we want to find the final velocity. Is it going to be negative or is it going to be positive? And again, the math will tell us who wins, right? Who's gonna be pushing who frontwards or backwards. So let's take a look. I know that I have the fullback traveling with a momentum of 600, and the lineman traveling with the momentum of negative 400, which means my total momentum before the collision is 200. It will equal the same thing at the end, so I know it'll equal 200 at the end. Since they stick together, they have the same velocity, so 75v and 100v. We solve for v, and we get 1.14 meters per second east, which means the fullback pushed the lineman to the east, and it was positive direction. Remember, if you got a negative answer, it would just mean the lineman pushed the fullback back. If you have any questions, see me.